Every single time you type a message, listen to some music, or even just look at a photo on your screen, you're using a secret language. You're having a whole conversation with your computer. But here's the catch. You don't speak the same tongue. Well, today we're going to crack the code and learn its native language.
I mean, really think about it. How on earth does a machine that's just a bunch of metal and plastic and silicon, how does it understand a human word like hello? It doesn't have a brain like we do. So what's really going on under the hood when you type those 5 letters?
Well, when we type hello, our computer sees this, a long, kind of jumbled-looking string of ones and zeros. See, computers can't understand our language directly. They see everything, and I mean absolutely everything, as numbers.
But that string of numbers isn't just random noise. Not at all. It's a super structured language called binary. And to understand it, all we need to do is crack the code by getting our heads around something called a base system.
So let's put these two languages side by side. On one side, you have our everyday system. It's called decimal, or base 10. Why? Because it uses 10 different symbols, the digits 0 all the way up to 9. Then you have the computer's language, binary, or base 2, because it only has 2 symbols to work with, 0 and 1. And that's the key right there. The whole secret is that the base of a number system is just a fancy way of saying how many symbols it uses. We've got 10, so we're base 10. Computers have 2, so they're base 2. It's really that simple. And yeah, as you can see here, other systems totally exist, like octal and hexadecimal. But for what we're talking about today, we're going to zero in on the 2 that really matter, our familiar decimal system and the computer's fundamental language, binary.
So to crack binary, let's just look at something we already know inside and out. In our system, where a digit matters, right? In the number 231, we all just know the 2 is worth more than the 1. That's because it's in the hundreds place, not the ones place. Each spot is just a power of our base, which is 10. It's something we do without even thinking about it.
Now, over in the computer's world, each of those ones and zeros gets its own special name. They're called bits, and that's just short for binary digit. A bit is the absolute smallest, most fundamental piece of information a computer can possibly deal with. It's like the atom of the digital universe. Okay, we've got the basic vocabulary down. So how do we actually do the translation? How do we take one of our base 10 numbers and turn it into their base 2 bits? It's actually way easier than it sounds. It's really just simple division. You take a number, like 13, and you just keep dividing it by 2, and you keep track of the remainder each time. Once you can't divide it anymore, you just read those remainders from the bottom up, and boom. Just like that, our number 13 becomes 1101 in binary. And going the other way is just as easy. Instead of powers of 10, like our system, binary uses powers of 2 for its places. So the 1's place, the 2's place, the 4's place, the 8's, and so on. You just multiply each bit by whatever place it's in and then add it all together. And that 1101 gets us right back home to 13. It's a perfect two-way street. All right, let's see this happen in the real world. Imagine you're at your keyboard and you go to press a key. Let's say you press the number 9. The moment you do that, I mean faster than you can blink, the computer's brain, the processor, does that translation. That 9 that you understand becomes this pattern of bits, 00001001. That is the only way the machine can understand what you just told it to do. And this is where it all starts to get a little bit mind-bending, because that simple process, translating our numbers into their numbers, well, it isn't just for numbers. It's for everything. And I'm not exaggerating. This simple language with just 2 symbols is the fundamental building block for every single thing you experience in the digital world. So, that letter A you type, to the computer, it's not a letter. It's just a very specific pattern of bits. Every word you write is just a longer chain of these unique patterns. And what about sound? The music you listen to, or even my voice right now? Yep, you guessed it. It's all just represented by these incredibly long streams of ones and zeros. Now, this is the part that always gets me. Even a complex, beautiful, colorful image is built from this simple code. The color and the brightness of every single tiny dot on your screen, every pixel, is defined by its own pattern of bits. It's all just numbers. So this all feels a little abstract, right? Ones and zeros flying around. What does that actually mean inside a physical machine? Let's peel back that final layer. The answer, it turns out, is beautiful in its simplicity. A 1 just means an electrical switch inside the computer is on, letting electricity flow. And a 0? It just means that switch is off, stopping the flow. That is it. On or off. Yes or no. 1 or 0.
So let's connect it all. Every letter you type is just a specific set of tiny switches flipping to on or off. The color of every single pixel in a photo is another pattern of switches. Every sound you hear, another pattern. Your entire digital life, all your messages, your music, your photos, it's all running on billions of microscopic switches, flipping on and off thousands and thousands of times every single second.
Just let that sink in for a minute. Everything we've seen, all the complexity, all the creativity, all the information in our digital world is built from just two simple states, on and off.
And that kind of leaves us with a pretty fascinating final thought, doesn't it? If our entire digital universe, with all of its incredible complexity and beauty, can be built from a simple choice between on and off, what parts of our human experience can't be translated into this language? What can't be broken down into ones and zeros?